CBE 360, this is an excerpt from Marlin's textbook, Process, Control, and Dynamics. Chapter 8 is called the PID algorithm. So, we're learning about the closed loop transfer function for a feedback loop. There's the disturbance response and there's the set point response. The only difference between these two equations is the input variable, so we have a disturbance and we have a set point. So in summary, the block diagram procedure for deriving a transfer function involves 4 steps. Select the numerator of the transfer function, the output. Solve in reverse direction to the causal relationships. Eliminate all variables except the numerator and denominator in the transfer function. Separate variables in the equation, divide by the denominator variable to complete the transfer function. Here, we can write the transfer function in terms of the deviation variable of itself. So the transfer function of p is equal to the deviation variable of the transfer function p times gv times gs. Just going to skim through the chapter really quick, just reading the highlighted points. The block diagram analysis yields several valuable results. The block diagram provides a visual picture of the equations showing the feedback loop. The general closed loop transfer function model can be applied to any specific system by substituting transfer function models for the loop elements, and entries into the overall transfer function denominator demonstrate that the only elements of the feedback loop affect the system stability, neither the disturbance nor the set point changes. Set point change flexibility. I'm not sure what stability refers to. I can go over here into the book and I can look up stability. So stability is introduced in chapter 4. So right here we have the highlighted word stability is the real parts of the roots of the characteristic polynomial ds determine the exponents a in the solution. These exponents determine whether the function approaches a constant value over a long time. And we must look carefully at the case of roots with a value of 0. If one distinct root has a value of 0, the system is stable. While if repeated roots have values of 0, the system is unstable. So the results are summarized below. Number. Okay, so right here, results are summarized. We have stability is determined by the roots. So only one root is 0, we have a stable system. And if 2 of them are 0, we have an unstable system. I've been going on a tangent for a while, so let's go back to chapter 8. So we have the proportional mode. I have no idea what that fucking means. We have example 1, example 2. So notice in example 1, we don't directly define the control variable. However, we just go straight ahead and say control variable differential in variable t as t approaches infinity. So this is basically the final value theorem. The final value theorem is stating the negative of the control variable differential is equal to error. And since the differential indicates that it's a change, so that change is the error, we have 3 CSTRs in series. So this is steady state value for error under proportional control, and it can be determined by rearranging the equation 8.11. Here we have an order, a third order. So we call it the valve transfer function is included in GP, and the center transfer function is assumed to be unity, implying instantaneous error-free measurements. So we make some correlations here. Applying final value theorem to the system with a step-like disturbance. Step-like was also deemed stepwise. No, it was just deemed step-like. So this step-like function is the most recurring case. And then we have the error function, and we have this correlation with equation 2, stating that we can add a s and then a differential of the input over s times the transfer function. So all we did was input the transfer function into this step-like disturbance. So note that the feedback control system with proportional control does not achieve zero steady state because it's not equal to 0. The final value theorem is not equal to 0. The negative final value theorem is not equal to 0. And this result can be understood by recognizing the proportional relationship between the error and the manipulated variable in the control algorithm. The only way in which the control equation 8.9 can have the error return to 0 is for the value of the manipulated variable to return to its initial condition. However, for the error to be 0 in the process equation, the manipulated variable must be different from its initial value because it must compensate for the disturbance. Thus, the steady state offset occurs with proportional only control. Next, we have example 2, and notice we just have a tank with a heater and we have a temperature controller. Right here, we do have a feedback. I guess we only have one tank, so I think the order is indicative of how many processes we have. So right here, we say that the GP, the transfer function of the process, is first order, transfer function of the disturbance is first order, and transfer function of the controller is first order. It's just KC. Notice that we don't have a sensor anymore. So right here, we have for no control, and then we have with a proportional control. And just to make a note, we're writing it in terms of transient variable. So I'm not sure if we transformed it back. I'm not sure what transient equations are telling us. I'm not sure what it tells us. Here we have the integral mode. Then we have the derivative mode. So PID, PI, and then P. And then we have the PID. So the PID controller naturally is desired to retain a good feature of each mode in the final control algorithm. This goal can be achieved by adding the 3 modes to get the final expression of the PID controller where the derivative mode appears. 2 forms are given, the standard and the form recommended in this book, because it prevents set point changes from causing excessive response as described in the preceding section. We have the time domain controller algorithm. We have proportional integral derivative, proportional only controller, proportional integral controller, and proportional derivative controller. So we're given the P controller, the PI controller, the PD controller, and the PID controller. Here we have the Laplace transform. The control algorithms are used often in the block diagrams and in closed loop transfer functions. In these analyses, the main purpose are to determine limiting behavior for control systems, so determining stability and frequency response, usually for disturbance response. Thus, the PID form with derivative on the error is used for simplicity. The transfer functions for the common forms are as follows. Note that each transfer function has the output over the input, with the input and output taken with respect to the controller, which is the opposite of the process. Also, since transfer functions are always in deviation variables. And then next, we're given analytical expression for a closed loop response. And then the importance of the PID. Notice that we have the manipulated variable of the control variable, showing the transfer function. And then we're given the conclusion. I'll read the conclusion. In this chapter, the important proportional integral derivative control algorithm was introduced, and the key features of each mode were demonstrated. The proportional mode provides fast response, but does not reduce to offset of 0. The integral mode reduces the offset to 0, but provides relatively slow feedback compensation. The derivative mode takes action based on the derivative of the control variable, but has no effect on the offset. The combination of the modes, or a subset of nodes, is required to provide good control interfaces. A few examples have demonstrated that the PID controller can achieve good control performance with the proper choice of tuning constants. However, the control system can perform poorly and even become unstable if improper values of the controller tuning constants are used. An analytical method for returning good values with the tuning constants was introduced in this chapter for simple first-order processes with proportional only controller and proportional integral control. And more general methods are presented for more complex systems in the next 2 chapters. The dramatic influence of feedback on the dynamic behavior of a process was discussed in chapter 7 and demonstrated mathematically in this chapter. Naturally, the ability to maintain the control variable near its set point is a desirable feature of feedback, but the potential change from an overdamped system to an underdamped or even unstable one is a facet of feedback that must be understood and monitored carefully to prevent unacceptable behavior. In chapter 4, it was demonstrated that the key facets of periodicity and stability are determined by the roots of the characteristic equation, that is, by the poles of the transfer function. For the 3-10 process without control, the characteristic equation is this 3-10 process. Third order, giving the repeated poles s equals 1 over tau. Negative 1 over tau. Since they, I don't know how it's repeated. Maybe it's repeated because it's the third order. Since they are real, the negative, the dynamic response is overdamped and stable. When proportional feedback is added, the transfer function is given an equation at 12, and characteristic equations as follows. Thus, the controller gain influences the poles and the exponents in the time domain solution for the concentration. The influence of feedback control on stability is the major topic of chapter 10. Finally, it is important to note that the PID controller is emphasized in this book because of its widespread use and its general good performance. The dominant position of this algorithm is not surprising because it evolved over years of industrial practice. However, in nearly no case is it an optimal controller in any sense, minimizing the integral of the absolute value of the error or the maximum deviation. Thus, other algorithms can provide better performance in particular situations, and some alternative algorithms will be introduced in this book after the basic concepts of feedback control have been covered thoroughly. So this is the last boxed off text. With models for process and controller now available, the dynamic behavior of a closed-loop system can be analyzed quantitatively. These questions provide some learning examples while using the mathematical tools available. Additional analytical methods are introduced in the next chapters. The key concept is the manner in which the process and controller both influence the feedback system.